When you pass light through a pair of slits that are in line with each other, you produce an interference pattern in front of the slits, with a very regular pattern. This arrangement is called Young's double slit experiment, and is used to show the nature of light. The light comes from a single source, in this case a laser, as the light is clearer and produces much more distinct fringes than an ordinary light bulb. The laser experiment is more dangerous, however, because the energy in a laser beam is the same as that of a light bulb, but much more focused and concentrated. A laser could damage your eye very quickly compared to an ordinary light bulb. The path that different light waves take through the apparatus is different to each other. The diffraction of the laser light through the slits makes different waves of light take different paths, instead of all the waves now travelling one path. We now have several waves travelling several paths. The laser light is still coherent, however. The path lengths are just different. One beam of light moves straight through our equipment and is not affected by the slit. This light makes the minimum distance to go from source to screen. Every other beam of light in the experiment takes longer, and so will arrive at the screen at different points in its wave. If the first wave hits the screen at a peak, the other waves nearest to it will not. We know that the wave hitting the screen has arrived there at a peak, because it has interfered with the other spread out light to form a brighter spot. This bright spot is constructive interference, and represents two waves meeting at peaks. We can say that the phase difference between these two waves that interfere to produce a bright spot must be a multiple of the wavelength of the light. Anything else would not result in a bright spot. As we move away from this bright spot, we move into a region of darkness. We know that this must be where a peak and trough have interfered, because this is a destructive interference pattern. The distance along the screen between the bright spot and the dark spot represents half a wavelength of the light. The difference in the path lengths of the two waves that come together to make this standing wave must be half a wavelength. If it wasn't, then the spot wouldn't be dark. We move on to the next bright spot, and we can infer that the phase difference that went to make this standing wave was zero. In order to make a dark spot in our interference pattern, the two waves must have differed in their path length by an odd number of half wavelengths. In order to make a bright spot, the waves that interfered must have had an even number of half wavelength path differences. If you had more than one source of light in this experiment, you could move it around to generate different interference patterns, in which you could infer the same properties. However, it is only the single source double slit experiment that generates the pattern of bright spot, dark spot, etc.